Okay, so good morning, good evening, good day, wherever you are, and welcome to MIT InnoTherm. I'm Chen. I will be moderating today's panel, and my colleagues, Oscar Henry, John Lenert, everyone were organizer for this colloquium series. And I think some of you probably in the series from the beginning, and this is actually the colloquial number 17. And today we'll talk about the high temperature direct energy conversion, including thermophotovoltaic and thermionic technology. But before we jump in, I just want to say we launched this colloquium during the pandemic, and we're really very grateful for people to attend those colloquium. We hope to bring people together during this difficult time. And we're happy to say that the colloquium so far has a very good attendance. I think it average was around 400 people, because we have about 6,000 people attending according to our record, and we had so far 16 colloquia already. So somewhere near 400 people on average. And also online, there are a lot of views. Our counter reset recently because we're migrating, but if you go to YouTube, you probably can see some of those really have very good views. So today this is a topic I think many of us are interested. And before we jump into introducing the people, I want to mention two stories. In fact, one is on thermophotovoltaic. The field was started by Dick Swanson, and Dick Swanson is, say, we know in US, probably the two biggest solar companies. One is SunPower, and he started SunPower, and so this is silicon-based photovoltaic. So actually, originally, if I claim from his work in thermophotovoltaics, at the time he was working on silicon. You'll hear more on this. And the other is on thermionic technology. Currently there's a company many of us buy scientific equipment from, this Thermo Fisher. And Thermo Fisher is a combination of two companies, Thermoelectron and Fisher, right? And Thermoelectron started by George Hatsopoulos. And he, at the beginning, was aiming to commercialize the thermionic technology. So we have this really great stories from starting commercializing TPV and Thermionics, and grew big companies, not exactly this technology. But today, we're happy to have really leading people discuss the ideas and the current status of this technology and the commercial efforts. So I'll introduce our panelists, Andrej, starting with in the order of today's presentation. First is Andrej Lenert. He's currently assistant professor at the University of Michigan and in chemical engineering department. He was a graduate from MIT Rosenau Lab. We're very proud to have him on board. And he received a 3M non-tenure faculty award and was named by Forbes as one of the 30 under 30. And his research area is radiative heat transfer, energy conversion, transport and storage, and the nanostructural materials. And after Andrej, we have Gerard Schwede, and he is the founder and CEO at Spark Thermionics. And he graduated from Stanford with a PhD and did some really interesting work in combining photon with thermionic effect. And he joined the Lawrence Berkeley National Lab as part of their first cohort of the cyclotron road. And his research area is energy conversion and heat transfer, semiconductors, and solar devices, micro nano fabrication. And he will talk about, of course, thermionics. And we have our third panelist, say Alejandro. He already attended this series as a panelist on thermal storage. And he is an assistant professor at Technical University Madrid. I couldn't really speak very well the Spanish, so sorry, Alejandro, you taught me, but I know. He's an electrical engineer, applied physics, and he has experience at the Tokyo Institute of Technology, MIT, and worked on thermophotovoltaic, thermionic, and high temperature thermal energy storage. So today he will talk about his idea combining these two technologies. So our game plan is we'll have these three speakers each talk about 15 minutes, and then we hope to use 30 minutes for Q&A. So this is a webinar. On your screen, there are Q&A button, and you can send in your questions along the way. And we hope to use more time to discuss after everybody's presentation. And if you want to have your name mentioned, we'll assume your name, we'll mention your name if a question from you, but if you want to stay anonymous, you can stay so, or you can just send anonymous comments. So after this, we'll post the recording on YouTube, and if there are questions we couldn't handle, as in the past, that's the most of the time it's the case, we will post all the questions on YouTube so people can continue the discussion. So with that, let me hand over to Andrej. Andrej,
all right.
Yeah.
Yes. Do you see my screen okay?
Yes.
All right. Well, thank you, Gong. Thank you for having me. I'm thrilled to be a part of this series and to be able to share with you work that really grew out of the Rosenhau-Kendall lab at MIT and talk about some recent advances in TPV conversion. I want to start off by acknowledging that this work that has been done recently in my group is really in collaboration with Steve Forrest and one of his students, Deju Fan, who were pioneers in developing new TPV devices, and also acknowledge my student, Tobias Berger, who is almost ready to graduate, as well as support for this work from a variety of sources at NSF, in particular EPMD and thermal transport processes, as well as support for some of Steve's efforts from the Army Research Office. So since I'm going first, I will give a very short explanation of how thermal photovoltaics work. And if you are familiar with a solar cell and how it works, you're well on your way. Just replace the sun with a local heat source, a hot emitter, and just take into consideration that that emitter is closer and takes up more of the solid angle. And so these devices have much higher power density. To heat up that emitter, we can use a variety of sources, including direct solar heating, fuel, chemical fuels, nuclear fuels, or even electrical heating. And I star solar and electrical because they were the topic of an earlier InnoTherm on May 13th, which discussed the Brayton battery and approaches that use high temperature thermal storage to take surplus renewable electricity, convert it and store it in that form before using heat engines to put it back on the grid. And one of the suitable heat engines for higher temperature storage are TPVs. So my talk today is going to mostly focus on the efficiency of this conversion scheme, and efficiency is an important metric at this stage and this technology readiness level. And there are other metrics that are important as well, such as power density and cost, but I'll focus mostly on efficiency. And efficiency can be thought of as the typical heat engine form, which is the electrical power that's generated divided by the heat that's consumed by the emitter. And we can also break it up into two factors. One is the absorption efficiency, which takes a look at how much of the energy that's absorbed is converted into electricity. And the cavity efficiency, which just describes how well radiation is transferred from the emitter to the cell. And I'm going to focus mostly on absorption efficiency. And recently we published a review paper in Joule that looked at efficiencies across the years. And one of the things that we found is that we have been making improvements recently, but also notably, and Gang mentioned this, back in the late 70s and early 80s, Dick Swanson really pushed the envelope in terms of conversion efficiency with his silicon TPV cells, which were able to reach about 29% absorption efficiency. Now looking at the progress, the focus of my talk today is going to be on these last two data points, in particular work out of UC Berkeley that was able to achieve 29.1 with an in-gas TPV cell, and work out of our group that was able to achieve 32% and was published earlier this year in Nature. And so I think if you were just to look at this progression of efficiencies, you may say that we haven't really come that far over the last 30 years, only a few percentage points relative to what Dick Swanson was able to do. But hopefully I'll be able to convince you today that if we dig a little deeper, we'll see that the future for TPVs is much brighter. And I'll be able to answer this question of what is the real significance of these recent TPV advances and provide some context for where we're going next. So to do that, it's important to look at efficiency as a product of spectral and carrier management, and to compare each efficiency point to its respective thermodynamic limit, which in this case is the radiative limit, and it only considers radiative recombination. And so spectral management describes how well the blackbody spectrum is utilized to excite carriers across a specific band gap compared to how much energy is absorbed by the cell. And carrier management describes how much power is produced relative to sort of the maximum ideal power that could be produced. And so it's a ratio of this blue square on an IV curve to this gray square. And if we look at TPV efficiencies along these two metrics and we compare them to the radiative limit, we see now that the recent advance in 2019 gained a lot of ground in terms of carrier management with respect to the Dick Swanson silicon TPV cell. And I'll show today that we were able to improve TPV conversion along another facet. And I'll be able to hopefully convince you that going forward, we should be able to combine these two to reach very high efficiencies. So the metric that we were going after in our group is to improve spectral efficiency. So the ability to convert this broad spectrum that's radiated by a heat source. And I just want to note, without going into too much detail, that TPVs are best suited at converting the thermal tail of the blackbody distribution or Planck's distribution. And that's because as we push the band gap higher, we can produce higher voltages, and then we're less susceptible to non-radiative recombination and ohmic losses. And these are very important losses in TPVs. So as we push the band gap higher, these become less important. But what we're left with is we have to manage a large amount of radiated power that's out of band, that's at energies below the band gap. Usually this accounts for 75 to 80% of the overall radiated power. So the approaches to do this, to suppress out-of-band radiation or radiative heat transfer, can be categorized as either emission suppression, so emitters that use structures or filters to suppress emission, or another approach is to reflect that low energy radiation selectively back to the emitter. And in terms of the efforts to accomplish this mitigation of out-of-band loss, which is so critical to efficiency, there's been work out of MIT to develop selective emitters. There's also been some more older work looking at front surface filters. So these are filters that are put on top of the cell, and that through interference and plasma achieve reflection across a broad band. And really the devices that have achieved the highest efficiencies rely on back surface reflectors. So these are really good mirrors that are placed behind the absorber. And this architecture is the one that was used by the Berkeley group to achieve 29.1% efficiency. However, looking at what's been done so far, what we see is that current strategies only suppress about 95% or less of this out-of-band power. And you may say that seems pretty good, but actually if we look at the sensitivity to this metric, what we see is that in the radiative limit and at these prototypical conditions, by improving the reflectance by a few percentage points, we can reach very high efficiencies. So at 95% reflectance, we're bound to 47% efficiency, but if we go to 100, we max out at 60% efficiency. And so these are large gains for marginal changes in out-of-band reflectance, so a key metric to improve upon. Our initial work in 2018 tried to do this by developing an architecture where an in-gas absorber was put on top of a low-index spacer and then on a mirror. And we were trying to improve reflection in this structure out of band. And theory suggests that the out of band reflectance should be close to 98 or 99%. But in practice, we saw parasitic absorption in this magnesium fluoride spacer. And this is something that we've noticed and other groups have seen as well, as there are issues once you start to actually deploy a dielectric spacer, a low index dielectric spacer behind the absorber. So we came across this bold idea of trying to replace the dielectric spacer with nothing. And when I say nothing, I mean air. So try to put a small air cavity behind the absorber and the back gold reflector. And now this geometry or this architecture, this air bridge architecture as we call it, can achieve lossless Fresnel reflectance at each interface. Air is, in a way, an ideal dielectric. It doesn't absorb, and it maximizes the difference in refractive index between the semiconductor air interface and the air metal interface. And so overall, we can achieve very high reflectance. And simulations show that that reflectance can approach 99%. And in the next couple of slides, I just want to show you how we achieved this fabrication of this device, how we realized it. And I want to demonstrate that it's relatively straightforward. And I expect that it's something that can be replicated in other labs, or at least I encourage people that it's something that they can accomplish as well. And so I just want to highlight the simplicity of the process for making this air bridge architecture, because there are similar architectures that have been reported, but what was used was a much more complicated process to make them. So we start by growing a epi layer on a lattice match substrate, indium phosphide, and we define the grid lines that will end up being the supports of the absorber of the air bridge. Then that wafer is flipped over and bonded to a planar gold mirror. And once that bond is established, we can etch away the parent substrate, the indium phosphide substrate that was used to grow the epi film. And then we can pattern out the cell and put a top contact. And the resulting architecture is shown here. This is a cross-section where we can see the active absorber layer suspended over the planar gold mirror over this air cavity. And we can achieve spans of close to 100 microns while maintaining the 600 nanometer air gap using this simple fabrication process. And now we can realize a reflectance, very high reflectance in practice that matches our simulations. So now the out-of-band reflectance is as high as 98.5%. And that high out-of-band reflectance should lead to high efficiencies. So to do this, we developed basically a TPV simulator setup, sort of analogous to a solar simulator setup. But here we're using a glow bar source at about 1450 Kelvin. And we can vary the illumination levels by changing the distance relative to the TPV cell. And what we see is that as we increase the illumination level and consequently the short circuit current, what we see is voltage gains up to some point at which ohmic losses begin to dominate, and then we see plateauing and even a downturn in efficiency. But at The peak efficiency, the peak absorption efficiency that we see in this device is around 32%. And the IV curves that are correspond to that 32% are shown here with an open circuit voltage of around 0.45. All right, so let's go back to this plot of spectral versus carrier management and see where we ended up. So our work pushed, as I mentioned, pushed into this high spectral management, high efficiency spectral management regime. And we made significant gains in that direction. And we were able to surpass and approach about 55% of the radiative limit. And I want to say that, I want to acknowledge that we pushed along different facets of this problem relative to the Berkeley group, but there's no reason why these two can't be merged together. And so if we were to come up with a hypothetical scenario that does this, I would expect that in the very near term, we would see single junction efficiencies at 1500 Kelvin for InGas that are approaching 40%, about 38%. And also I want to acknowledge that this is single junction efficiency. Efficiencies can be higher for multi-junctions. And there's work out of NREL at MIT that have shown about 36% absorption efficiency with a multi-junction cell. And they, using their models, they estimate that if the reflectance goes to 98%, they can exceed 40% efficiency. So this paints an optimistic picture, but I want to paint an even more optimistic picture by saying that the air bridge architecture allows us to now think about operating in an entirely new regime, device regime. And this is best shown by these bands, gray and blue bands, that are on a plot of spectral efficiency versus band gap divided by the thermal energy of the emitter. And what I want to say is that these gray bands show the trajectory of efficiency, spectral efficiency, as a function of increasing band gap or decreasing temperature. And if we are in the conventional reflectance regime, as we increase band gap, we take a hit on spectral efficiency. But if we start to approach above 98 or 99% reflectance, which can be enabled by the air bridge architecture, we see that we enter a regime where we're much less sensitive to band gap and temperature. And so this opens up a very exciting possibility of using cheaper, wider band gap cells that have already been produced for solar applications, or enabling the use of lower temperature heat sources. And I think both of these are very exciting as a path forward for TPV technology. So I'll end there and turn it over to Jared. Whoop. Sorry, I'm just trying to end my screen share.
Okay, I hope everyone can see my screen.
Yeah.
Great. So it's a pleasure to be involved in this panel, so thank you so much for the invitation to be here. And today I'm going to be presenting a general introduction to thermionic energy conversion, and within the context of this panel to explain some of the differences, similarities to thermophotovoltaics. So you might not be familiar with thermionic energy conversion, but you're actually quite familiar with devices that use thermionic emission. And it's just a source of electron evaporation. So if you remember your old CRT monitor, there's a little filament that gave off electrons that were rastered back and forth. And if you have fluorescent lighting above you, there's thermionic emission going on above your head. At the end of this, there's a little filament that's giving off electrons that then help excite the mercury within the fluorescent bulb. And so what we do is we use this electron evaporation as a direct source of DC current. So instead of a filament, we have, in this case, a plate that emits electrons across a small vacuum gap that is close to another material, which we call an anode. So this thermionic cathode emits electrons directly across this gap to this anode, and that's a source of DC current. So thermionics actually has a very long history that Gong alluded to. And in the 1960s, as part of the space race, multiple groups were achieving mid-teens efficiencies, really enormous power densities, above 10 watts per square centimeter. And in those days, the leading folks in the field, that's the Hatsopoulos that Gong alluded to at Thermoelectron, and Wilson was at GE, believe that there is a ton of potential left on the table for these thermionic energy conversion devices. So what happened? Well, what happened was they got captured by a single application, that was deep space nuclear power. And within that single application, well, efficiency matters, but it wasn't necessarily the most important. It was one portion of a system. And at the end of the day, the only interest from that was from NASA, and NASA had a good enough solution, which is great for NASA, which is thermoelectrics. And so in the case of deep space nuclear power, thermionics lost out. But that means that today there's an enormous opportunity to apply decades of innovations and materials and microfabrication that I'll describe a little bit in general later in this talk. But before I do that, I just want to give folks a status of where conventional thermionics got to, because I feel that much of this early literature has not been looked at in the last couple of decades. So here you can see the characteristic curves, the efficiency that was possible in the 1960s, and in the 1990s, there were vacuum chamber measurements that put the efficiency around 20%. The power density and what temperature was required for that power density you can see here. But for me, the most important thing perhaps is the lifetime. That in the 1960s, they figured out a lot of the metallurgy and showed that there was no fundamentally life-limiting mechanism for thermionic converters that was present now. By 1973, there is a 5-year lifetime test that the device was operating the same at the end of that test as it was at the beginning, as you can see here. And in the 1980s, as part of the DOE work, they demonstrated well over 10,000 hours in a combustion environment with really enormous year-over-year change. So that's where we come in. Spark was founded in 2015, and it was really based off of a lot of the work during my PhD at Stanford and those of my Stanford colleagues. After I graduated, we became part of the founding cohort at Cyclotron Rhodes, spun in to Berkeley Lab, at which point we gained support from RPE and also from DARPA, as well as some of our first investment. And using this RPE support and this other investment support, we were able to demonstrate first fully encapsulated devices, which resulted in our first sales in 2019. And if anyone would like to test some of these thermionic devices themselves, feel free to reach out. Since that time, we've expanded from Lawrence Berkeley Labs, spun out into our own facility at Emeryville, California, still quite close to just a couple of miles from the lab, and we still maintain active collaborations there. And while I won't have too much time to talk about them today, I did want to mention that there's been continued work by Ian Lim and collaborators at Lawrence Berkeley Lab, by Andrej and Andrej Schwede. And this work was focused on understanding electron reflection in these thermionic converters and then minimizing it with nanoscale order. And since that time, we've also gained the support of the Army, Air Force, increased our collaborations outside of the lab to Army Research Lab and most recently Oak Ridge, and also have received continued support from California Energy Commission as well as the DOE. So going a little bit more detail in terms of the basic operations, the emission current follows what's known as the Richardson-Deshman equation. And as you can see, it's a very sensitive function of the work function of that cathode. In terms of the voltage that we get out, in the ideal case, it's simply the difference between the cathode and the anode work function. However, in reality, electrons have charge. And so once they begin to emit into this vacuum gap, there's typically some amount of space charge that builds up that begins to suppress that emission current. That means that you often have to apply some voltage, accelerating voltage within the gap in order to mitigate that space charge. And that brings us to the basic figure of thermionic devices, which is the sum of the voltage within the gap, as well as the anode, sometimes called the collector work function. So this is known as the back voltage or barrier index. And I'll be spending a couple of slides now kind of describing what the opportunities within this are. So you can essentially just write down what is the possible efficiency of a thermionic device as a function of temperature parameterized by this barrier index. And the historical folks were typically at barrier indices around 2 eV. However, that was, as we'll describe, part of the limitations of the technology of the day. It's quite straightforward to create a work function around 1.5 in an operating device, and in a vacuum chamber, it's very easy to get down below 1, and I'll highlight some of those as well. So what I want to emphasize here is, while it's very challenging to integrate these barrier indices, integrate these low work function materials, it's not at all crazy to be talking about a barrier index of half a volt to a volt. And in fact, we've demonstrated work functions as low as 0.6 eV. This would be, if you're familiar with thermoelectrics, competitive with a ZT of 10. It really shows the potential for the opportunity for reducing work function and reducing this voltage that we have to apply within the gap. So because this is a panel that compares thermonics and thermophotovoltaics, I wanted to give a very brief discussion on what the sort of differences are between them. Because probably from a black box approach, you're saying, well, one side's very hot, the other side's cold, electricity comes out, and at least until recently, the performance in terms of raw efficiency is actually quite similar. So what I want to emphasize is that both thermionics and thermophotovoltaics depend on a flux of either electrons or photons above some threshold energy. In the case of thermophotovoltaics, that's often a band gap or the desired spectral emitter, and within the thermionic field, that's the work function of the cathode. And so I just wrote down the basic stat mech derivations of what that actual flux is. And you can see there's some dimensionless integral from some threshold energy, and then a bunch of constants in front, where we've made this unit list so that all the constants are at the top. And what you can see is that they share a lot of similarities. These constants basically have to do with the density of states of electrons and photons interacting.
We couldn't hear you.
Oh no, when did this drop out?
Now it's okay now, it's okay, okay.
Okay, so to summarize, I don't know when I dropped out, but there's some unitless integral and some unipole constants in front that have to do with the density of states as these photons or electrons are traversing the vacuum. And if you just divide these prefactors, you end up with mc squared over kt. So the thermionic version of this is about 1,000,000 times larger than the thermophotovoltaic. And what that means is that despite the black box similarity of these technologies, we're actually operating in very, very different regimes. As you heard in the previous talk, a band gap in a thermophotovoltaic cell is often just a handful of KT, and of course the voltage out is just a few KT as well, KT hot, I should specify. And at the typical emitter temperatures that you'll see in literature, of course these can be much higher for energy storage applications. You're looking at a pretty small band gap, as Andrej reported, of 0.6 to 0.75 eV. And this really forces you to operate at a very cold collector temperature, which has implications for system level design and efficiency. In contrast, in thermionics, as long as you can get them across the band gap, we have more electrons than we know what to do with. So the space charge is the critical thing to overcome. And then that barrier index tells you, for these electrons, of the heat that they're carrying from the cathode of that voltage, what fraction is actually converted into useful power. And so this barrier index is a primary challenge for reducing the thermalization loss of electrons coming from vacuum and then thermalizing at the Fermi level. It also means that for the time being, as we're still developing ultra-low work function materials, we're extraordinarily insensitive to the rejection temperature T cold, which has, again, important system level implications. So now I just wanted to cover, and I'll refer to a forthcoming review and a couple of slides. How is it that you can actually achieve a better barrier index? And this is a simplified energy diagram that's got a typical work function at 1800 Kelvin for historical thermonic devices, and typical anode and voltage in the gap for these historical plasma-based thermonic devices. So the first thing to know is that the ideal gap size for a thermionic device to mitigate space charge is on the order of a few microns. 0.5 to 5 is all pretty good, which was very difficult to achieve in the 1960s. And so instead they relied on plasma-based space charge screening, which worked incredibly well, but it did require a 0.5 volt overpotential in those days. What that means is that if we can reclaim that, we can go from here to this maximum power point, which directly increases the voltage, and voltage, all the other things being equal, directly translates to efficiency. There are several ways to do this. I don't want to stress that ideal, the micron gap size is the only way. There are schemes to improve plasma-based screening that folks have looked at. There are also gate-based designs, such as this one you see on the left. But we're focused on this microgap technique. And on the right side, you can see some of our data. This shows that for the first time, we can actually get power densities that are of relevance for thermionic devices. Fitzpatrick in 1993 achieved a 10 micron gap, which is fairly good enough in order to get a reasonable current out. And what you can see is at a very low temperature from a historical thermionic perspective of about 1300 Kelvin, or just above 1000 Celsius, we're able to achieve with micron gap spacers over a watt per square centimeter, which, as I'll refer to later, is a very important threshold. And I'll remind you again that this was just with conventional thermionic materials. Both emitter and collector in this case were just molybdenum with a low work function coating. But of course, we're not limited to chunks of refractory metal with coatings. There's several decades of materials innovation that now we believe that we can apply to this. And like I said, there's in principle no known reason that we can't achieve this low work function of 0.5. And like I said, we have personally achieved 0.6. Of course, it's a very long road between that vacuum chamber demonstration and getting that stably into a device. And I'll just highlight a few of them here. There are a few schemes in literature in order to use conventional coatings, but then shift the Fermi level within the device, such as here with backgating in a graphene collector. And while it shares some differences, and you'll hear more about it in the following, I also look at techniques to combine thermophotovoltaics and thermionics as part of this Fermi level splitting and shifting, because at the end of the day, it's all towards increasing voltage. But there are other techniques as well. There is a lot of work that has been demonstrated in diamond, for instance, that gets work functions within this low level. But I will mention that these will be limited currently to fairly low current densities, and that should be an active area of research to overcome. So I did want to mention that there is a forthcoming review that that should arrive in just a few weeks at this point. It's been accepted into advanced science. And the major purpose is, besides reviewing some of the most recent work, some of it was highlighted on the previous slides, is to define a core efficiency. Our goal there is to include realistic thermal pathways in practice, to both standardize it across different work, but to also discourage overly optimistic reporting of experimental results. And I'll briefly go through what that is on the following slide. And based on those thermal pathways, we identify a rough threshold of on the order of 1 watt per square centimeter as a region of interest. If you can get above 1 watt per square centimeter, we think that this is practical. But if your concept will struggle to get to that level, it's really difficult to justify integrating that into a practical, final, encapsulated thermonic converter. And the final area that we wanted to do is that we feel that a lot of the thermionic literature is just not as well known. And so while there are some very good plasma reviews in the early 1990s in particular, some of the work since then has not really appeared in too many reviews. So we wanted to highlight and unearth some of the recent, but also some of the more lesser known work over the last 20 to 30 years. And I'll just briefly explain why we think it's so important to consider a core efficiency, which is that there are a number of additional thermal pathways within a practical device. Here we've picked emitter and collector materials that are typical for historical devices. This somewhat exaggerates what I'm about to say. But there's radiation. If you're using, say, a cesium plasma, there may be vapor. There is conduction between basic encapsulation as well as any structures or spacers to structure the emitter from the collector. And all of these can be on the order, it depends on your design, of 1 to 10 watts per square centimeter, which is where this 1 watt threshold basically comes from. And while many report this lead in radiation, some recently have started to report just an electronic efficiency. So ignore all of these thermal pathways and assume that electrons are carrying all of the heat from the emitter to the collector. And we recommend against this because we think that it overstates the potential and also points you in a direction towards a lower power density as opposed to a higher one. And so I won't go too much into these individual curves, but what you can see is that if you only focus on the electronic efficiency, you could be very excited about a, say, a 30% plus efficient device. And I'll just mention that these are typical IV curves for microgap devices, and we picked a 10 micron gap to exaggerate these effects. But if you look at what actually happens when you include radiation or vapor, you could be at 13%, if not below 10, once you consider these thresholds of these devices. So the summary is that devices with very high power density tend to be able to overcome these parasitics much better. But in addition, the system has to be considered. And this also means what's required for cooling, or if you're fueling it, what pumps or blowers will be required for supplying that fuel to your device. So there's too much to talk about, so I'll just summarize here. So the first is that thermionics has a very long history of development to build from. Compared to TPV, there's very high power density that's possible, and flexibility and heat rejection, which is important for system level performance. But today, I think there's an enormous opportunity to apply materials innovation and modern fabrication in order to really unlock it and get past the sort of teens to 20% that was possible in the 1960s and 1990s. We've also hopefully convinced you that a core efficiency to standardized reporting to literature is important, which also sets a threshold of 1 watt per square centimeter as a target for these new concepts. And for additional information, I'll point you to this forthcoming review. And that's all from us. Thanks for the opportunity again to speak to all of you.
Thank you. We'll have Alejandro.
Thank you, Gang. So let me know if you can see my screen, please.
Yes, yes.
Okay, perfect. We have had very interesting talks about thermionics, thermophotovoltaics, so my role will be trying to put these things together. So I will talk about the concept of thermionic enhanced thermophotovoltaics. That is a concept that has been proposed very recently in the last few years. And I will start with a brief introduction. And you probably noticed that the previous two talks about thermophotovoltaics and thermionics have also focused on different metric figures. In the case of thermophotovoltaics, the main metric was efficiency. In the case of thermionic was power density, and this is related to because each technology is performing better in each of these metric figures. So I'm illustrating here efficiency as a function of power density for two technologies. One is thermophotovoltaics, and the other is thermoelectric generators. I'm not including thermionics here because of the lack of data in the literature. So the review that Jared is preparing will be very nice to complete this graph. But we could say that thermionics will lie more or less where thermoelectrics technology is represented in this figure, with the difference that thermionics typically operate at extreme temperatures much higher than 1007 degrees Celsius. But in general, you can see that, thermophotovoltaics performs very well in efficiency. You have here these two recent results that Andrej just commented, with efficiencies already over 30%. And thermionics or thermoelectrics as well perform very well in power density, but not as good in conversion efficiency. And we can understand this behavior very easily if we look at these two devices, thermophotovoltaics and thermoelectric converters, and how they are arranged. For instance, in the case of thermoelectric generators, you have a direct contact between the hot side and the cold side. So it means that there is a huge flux of energy carriers, and those energy carriers could be useful or useless. But at the end, there is a lot of them, and then the power is huge. But because there is a lot of carriers, in this case, photons that are conducted from the hot side to the cold side, this brings a lot of heat losses, and then the efficiency is limited. Well, the strategy in thermophotovoltaics is completely different. Here you have a possible arrangement where you have the hot emitter and the photovoltaic cell, and you place a filter in between them. Also, you could use a backside reflector, as Andrej commented in his presentation. But the aim at the end is to have a very restricted spectral band of emission that is reaching the cell. So the net radiative transfer between the emitter and the cell is restricted to very narrow range of energy photons. So it reduces quite a lot the power density, but it enables to use high bandgap materials. And well, the tendency to increase the efficiency basically is to make this spectral control as efficient as possible, and this enable to use higher bandgap materials. But this again increase the efficiency. That's okay, but the power density is quite limited. Typically, it's lower than 1 watt/centimeter. So the question now is whether we could go to this region here. So the question will be if we can develop devices that can operate in this region, very importantly at low temperatures, where most of the thermal application exists. Because obviously you can reach this region if we operate the TPV cells or the thermionic converters are extreme temperatures. For instance, if we go to 2000 degrees Celsius, we can operate in this region. But we want to do it with low temperature heat sources where most of applications exist. And this is what my talk is going to be about. There is a concept that is has a potential for approaching this range or this region of high power density and high efficiency, and this is near field thermophotovoltaics. The idea that was established in the early 2000s, so it has been already 20 years around, is that you can place a thermal emitter very close to a photovoltaic cell, so the gap between them is very, very small, nanometric distance. In this case, if all the radiation sources inside the emitter, typically they are, some of these modes are totally reflected, internally reflected in this material. But if you place these two materials very, very close, then there are some photons that can tunnel this gap and then be absorbed at this site. If in this site you have a photovoltaic cell, then you can produce power out of this near field radiation. So you have a contribution of evanescent waves, which enhance the radiative transfer. And very importantly, you don't have any phonon propagation. So there is no heat conduction because the hot side and the cold side are interrupted by a nanoscale vacuum gap. So only photons can cross this gap. And well, very recently, there have been very encouraging results, as for instance, in this publication by Fiorino in 2018, where you can see that when you reduce the gap's distance, then you have a drastic increase in the power density, in the power output of the device, in this case up to 40 times when you reach distances as low as 100 nanometers. Well, just to make a brief overview of the state of the art, I'm writing here the 4 main experimental results proving this concept. This is the one that I saw before, but there have been other 3. And remarkably, I want to emphasize the date of the publication. So these are really, really recent results. So you have different EV cell materials with different bandgap energies, from extremely low bandgaps of 0.2 or 0.3 electron volts to more convenient, perhaps, bandgaps of 0.74, 0.67 for germanium. You have also the distances around 100 nanometers. This is the separation distance between the emitter and the cell. The temperature gradients between the hot and the cold side, so the cell and the emitter, are around 800 Kelvin in this case, in the publication of Inoue. And the power gain is in the range of 10, 40, or something, well, in that range of 1 order of magnitude power enhancement. And the efficiencies are, of course, very low for the moment, except for this publication in this LHC thesis in this year that represent the record conversion efficiency for this technology. But the rest of the publications are reporting very low conversion efficiencies for the moment. But I want you to pay attention especially to these two parameters, which are the size and the power that is produced by this experimental proof of concept. You see that the size is extremely small, so all devices are very, very small, and consequently the power that is produced in the near field is also very, very small. So you can imagine that there are reasons for making very small devices. You see all the implementations of these publications here. Well, you can solve planarity issues and things like that. But there is another key challenge of making these devices at larger scale, which is the ohmic losses, and this is what I'm gonna try to explain now. Well, if you want to make a near field TPV device at large scale, let's say 1 by 1 square centimeter device, well, you will need to incorporate some electrodes in the cell. I have figured out here one possibility, which is to place the electrodes in the front side. Of course, they have to be hidden, let's say, from the meter in order to be able to create this small distance. So at the end, well, you have photogeneration, of course, and you have a collection of electrons and holes in these two electrodes. Well, if you do the simulation of this device, you can get this curve here for the power density that increase substantially when you go below 1 micron distance, and then up to 6 watts square centimeter. But you have to pay attention to the current density, because we are using in this case a very low bandgap cell of 0.35 electron volts, which is needed to tackle the spectrum of the emitter, which in this case is 1000 Kelvin. So you need very low bandgap cells. And then, well, you will have huge current densities to produce these powers in the range of 10 to 40 amperes per square centimeter. And this is, of course, very challenging regarding the electrodes. So if you incorporate typical ohmic losses for these electrodes of 10 milliohm square centimeter, then you get this real performance of the near field TPV device. So you see that you lose quite significantly the capability of increasing the power density. So this points out a problem of scalability for near field TPV devices. I want to remark that I have made this for front side electrodes, but this will apply also if you make the electrodes on the rear, because at the end, the problem with the ohmic losses is the lateral conduction. So this trajectory of the minority carriers, when they have to travel to the local electrodes, is the main contribution to the ohmic losses, together with the conduction, of course, through the metal grid. So, and here it comes the idea of making this hybrid of thermionics and thermophotovoltaics that has a particular interest for applications in the near field. So here is basically the idea. If you want more details, you can read these publications. But the idea is that you allow the emitter to emit also electrons, so not only photons. So this is like a thermionic, regular thermionic device. But so you have these two energy carriers, you have electrons, and you still have photons as well. So the process at the end, what you have is that electrons are collected in the front surface, and they are injected in the valence band of your photovoltaic cell. So all the holes are recombined with these electrons in the surface, and then the electrons are collected in the back. So you need a P over N photovoltaic extractor. If you look at the results, if you assume work function for the emitter of 1.3 electron volts, so it's very low in order to tackle this low temperature operation, and anode or collector work function of 1 electron volt, so it's 0.3 electron volts of difference, you can get this power density, which, well, you can see that is quite significantly higher than what you can get in the real near-field TPV device. So the idea is that with this concept, you avoid any electrodes in the probe. So there is a wireless electrical connection between the meter and the photovoltaic cell. There is 1D carrier collection, and this is really, really important because 1D carrier collection avoids the lateral conduction of minority carriers in the photovoltaic cell, and then it enables negligible ohmic losses. And of course, you also have an extra thermionic power, which is basically due to the voltage that is established between the emitter and the front side of the cell. So then you get this much higher power density. Well, so we have done the first experimental proof of concept in a collaboration with the CNR in Italy. This is the setup that our Italian friends have in Rome. Where you can see this is the cathode, which is heated by a laser source. And here there is the anode, which is at a macroscopic distance here. So you can approach the cathode to the anode to a distances like a few hundreds of microns, not much less than that. You can see the results in this paper that has been published very recently in ACS Energy Letters this year. And the summary of the results are here on the right. Well, you have the current versus the voltage. Of course, this is the logarithm of the current. And you have the IV curves for 3 different devices. This device A is simply conventional, let's say, thermionic converter, where you have tungsten as cathode and P-type gallium arsenide anode. You have this other converter, which is already this thermionic enhanced device or photovoltaic anodes, where you have a P/N junction of gallium arsenide and again tungsten emitter, and an improved version of all of them, which is the C option, where you have the same photovoltaic anode, but this time with a cesium coating to reduce the work function of the anode. And you can see that, well, in these IV curves, you see different things. First, well, this is the direct operation regime, where you can see that all devices have the same saturation current, so they can be compared. So in terms of thermionic current, they are identical. This other side is a reverse operation regime, where you see that these 2 devices have the same current because basically they have the same surface properties. So it's tungsten and P-type gallium arsenide in both cases. But in this other case, you have a higher reverse current, basically because you have this other anode surface treatment where you have cesium, and then you have a higher reverse current. So the current that goes from the anode to the cathode. But the most remarkable thing is the voltage improvement. In particular, if we look at device A and B, we see that there is an increase in the voltage. For the same current, you get higher voltage in the case where you have a photovoltaic anode. And this voltage is even higher if we use cesium on top of the photovoltaic cell due to the reduction of the work function. So this represents basically the proof of this concept. And I will go very, very briefly. Obviously, I'm not going into the details of all the symbols in this graph, but the basic idea, this is the Venn diagram of this device, is to illustrate that you have a photovoltaic cell from here to right, and you have a thermionic device from here to left. And the 2 contributions to voltage are the thermionic states voltage here, which is basically the difference between the Fermi levels in the cathode and in the anode. In this case, this is a P+ gallium arsenide layer. And then in the photovoltaic side, you have this other voltage, which is the difference in the quasi-Fermi levels of the photovoltaic cell. So at the output, you have this higher voltage, which is the addition of these other 2 voltages. And that's basically represents well, what we have seen here. This is the increment that we see from the thermionic stage alone to the thermionic plus photovoltaic cell combination. Well, of course, this is a proof of concept, and there are a number of challenges to be addressed in the future. One of them is to establish large area nanogaps with very low thermal conductivity that withstands large temperature gradients. And we have seen that Jared have shown that they are working on that, and there is an interesting link here between thermionics and near-field thermophotovoltaics. In thermionics, typically, they need a bit larger gap distances of typically greater than 1 micron. But there is well, an interest in reducing this distance to get more power, and then you have, in the thermionic side, you have a problem with the near field radiation. So the idea is that having this hybrid concept, you can take make a good use of these photons that otherwise were wasted. Of course, the very important spectral control in the near field, you can take advantage of resonances in the surfaces, plasmon, phonon, polariton. You can also use real reflectors, so the work by Andrej could be also applied to this concept, basically, to improve the spectral management of the cell. And as Jared said, lower function materials for the cathode and the anode is very important. And obviously, at the end, the size system configuration is to make high temperature and high vacuum standalone devices assembly. So just let me acknowledge our funding program from Europe, Horizon 2020 program, FED Open. This is a Amadeus project that ended in 2019. And make one announcement, because we are having a symposium on thermophotovoltaics in EMRS, this spring meeting, in May 31 to June 4th. And there the abstract submission is open already until 19 January. So this is all. Thank you very much.
Thank you all for all the three really very stimulating talk. I would like to ask our panelists to turn on your video, and we will answer questions. If you have questions, please input your questions through Q&A. And I want to also make two announcements before I say, because some people may have to leave. This will be our last colloquium this year. So we will restart the new colloquium in 2021 on February 3rd. So that's our new semester start, and we will also say the next semester all the colloquia will be bi-weekly, and it will be say the same time, but it's on Wednesday rather than Tuesday. We have to juggle through our teaching, so that's why the change. So look forward to the announcement. And with that, let's go back to the questions. And let's say we have a few questions already. So I'll first, I think the first two questions actually was more geared towards Andrej, so I'll combine them. And one is from an anonymous attendee. How would you comment the effect of air property change when it's heated up and passed through by electric current? So that's and then the second question is from Anina Napoleon, and she asked, thanks for the very interesting presentation. A question for Andrej on the measurement efficiency. Is the efficiency measurement done at the full intensity at the emitter temperature, or is some percentage of the full intensity for your spectrum?
All right, yes. And for the first question, the air properties, the cell has to remain relatively cold. So we're not planning on heating up the cell to very high temperatures. During processing is probably the highest temperature it experiences. That's around 150 Celsius. during the bonding process. So there is air that's trapped in those cavities, and it can survive that temperature range. And hopefully that addresses your question. Sometimes a question about thermal resistance comes up, and it turns out that a simple back of the envelope calculation will show you that thermal resistance through that air is not that significant, and most of the heat flows through the gold grids, just as the charge flows through the gold grids. And in terms of the other question, yes, our TPV simulator does not reach full solid angle illumination of the cell. So that's one of the compromises that we had to make in the design of that variable illumination experiment. One of our goals was to really make TPV efficiency measurements accessible to a broader audience. I think if the buy-in is to have to develop a large-scale prototype in order to characterize the device, I think that's too high of an ask. And so I think there are steps along the way and milestones along the way that can be proven out. And I think that's the intention of our TPV simulator experiment.
Great. So we have a question for Gerard. How come the temperature of collector is ignored in thermionic emission performance calculation? Doesn't cause a back emission if it's too high?
Yeah, that's a great question. So it does cause back emission if it's too high. The rule of thumb is that emission turns on at 700 Kelvin per EV of work function. So if you're at a conventional material that's at, say, 1.5 EV, that means you can largely neglect back emission until you're at something like 1000 Kelvin. So that's really what I mean about this being a very insensitive, is that the performance is quite similar, and I'll be mixing going back to Celsius, but the performance is quite similar whether your collector is at 400, 500, 600 Celsius, and actually that 5-year lifetime data was at 800 Celsius. Now, as we create better and better collector materials at 1 EV, of course, you'll need to lower that. If you get all the way down to that half volt, you'll need to have similarly cold collectors as in thermophotovoltaics. But for the immediate future at practical work functions of 1 to 1.5, we can easily handle hundreds of degrees above ambient, which creates a lot of advantages in terms of the overall system.
Thank you. I think the next question is from Mohammed Taha Manzoor, and just a general query: can the emitter be designed to emit only in the desired wavelengths? I guess this is Andrej, you mentioned this probably, yeah.
In theory, yes. In practice, it's very difficult because you have to also operate the emitter at high temperatures, at which point the emissivity out of the wavelength range that you're interested in grows, particularly if you rely on a doped semiconductor or metal emitter. Then the emissivity increases with electrical resistivity, and it's really hard to control in practice.
Thank you. So we have a question from Lin Xiao Zhu. Thanks for the exciting presentation. This is Lin Xiao Zhu from Penn State. I have a question on the combination of thermionic and thermophotovoltaic. Would the electron bombarding in thermionic operation need to material degradation on the PV cells? So this is Alejandro. If you could you answer? You are muted. So.
Yeah, sorry. Well, maybe this is a mixture between Jared and me because, well, I can't tell much about the reliability of thermionics. Probably Jared can tell. In the anode, which is, well, the main difference of this combination is the material that you use to make the anode, and you are using, well, we are using gallium arsenide now, but that means that we are using that in the future. Because it could be germanium, it could be indium gallium arsenide, basically 3-5 semiconductors, or, well, if we go to extreme temperatures, why not silicon as well? So we haven't done any test of this reaction well, we have used cesium with gallium arsenide. We haven't seen any degradation after the experiment, but there could be some reactions there. I think Jared will comment on that. But well, at the end, in the PV cell, you typically also have a window layer to prevent recombination on the front surface. So you can use materials like amorphous silicon or even, well, some transparent conducting oxide. So you have a quite flexibility of designing your anode, even if it is photovoltaics, in order to reduce this interaction with whatever thermionic coatings you can place on top of that.
So since I will continue on thermionic question, and one from alumnus attendee, I wonder how important the lead loss would be in practical thermionic system.
Great question, and I didn't allude to that, and I'll also point folks to this review with our longstanding collaborators at UPenn that's forthcoming, Igor Bargatin and Matt Campbell. The short story is that you choose the lead based on the other heat flows within the device. Typically, you use a metal which is usually limited by Wiedemann-Franz. Of course, you could do better if you had a nice p-type semiconductor to create this into a thermocouple leg. But if you're using a typical metal that's limited by Wiedemann-Franz, then you have a trade-off between how much resistive loss that you want and how much heat conductance. And as a rule of thumb, you can imagine that you lose about 10% of each. So the voltage that you measure versus the voltage that you get out, it's on the order of 90% of that. And you only want to add a 10 or 20% additional heat flow through this as well. But the way that you do this is that you basically just decide on the dimensions of your leads. If your emitter is some distance from whatever collector insulating seal, then maybe you want a thicker or thinner sheet of metal essentially connecting the top to the bottom.
So that's great. So let me group a few thermophotovoltaic questions. And then there's a very important question I want to bring up later on. So see, one of this question is from Nima Talazadeh. What's the key point to have a less expensive TPV system to be successful in the market? And actually, say, let me combine this with another one, and because we're talking about market. Would it be possible for each of these of you comment on economics and most likely application of the technologies?
Sure, should I start, Con?
Yeah.
Okay, so in terms of the economics, so usually the biggest lever that people use in the economics of TPVs is power density. And that's a way, as you increase power density, the dollar per watt metric will go down. And that's been the main driver to bring down costs, and why semiconductors that are typically too expensive for solar applications would be considered for TPV applications is because of a 100-fold difference in power density. I think the other question was, just generally about why you would want to make it cheaper. So by going to more established technologies with wider band gaps, you can certainly make it more cheaper, and you can access production at larger scales, which is one of the bottlenecks to entry into an application space like energy storage, where you need to deliver very large systems. I think that would be probably the most exciting first application for TPVs, but realistically, there are other lower hanging fruits that don't actually depend on cost as much as power density or the weight of the device in aerospace applications.
Okay, Jared, do you want to go?
Sure, and I think Andrej covered it quite well. And this is also why we point very much towards the power density, because as long as you are still using high temperature materials, even if the materials themselves are cheap, the processing and putting together a high temperature emitter that's, say, compatible if you're interested in a combustion environment is quite challenging. It's actually a big focus, and I wanted to mention that this is the purpose of our California Energy Commission grant is to start scaling up the production of our converters. So I just wanted to give them a shout out that it's a really interesting program that I hope is replicated in states outside of California as well. The final thing that I'll just mention is, just like Andrej said, it's making power in difficult places that really depend on size, weight, and power. And so this has been a lot of our interest from the Department of Defense, whether it's the Army or the Air Force, is that if we're successful, this power density means that we'll create the smallest, lightest generator on the planet. And that has, which is, by the way, silent, and that has certain interesting defense applications for our first applications.
Alejandro, you want to say something?
Yeah, well, it has been very well covered, but the question is really important. Perhaps it's the most important question, if we can make this economical. Well, just to maybe summarize what has been said, I see three strategies to reduce the cost. One is increase the temperature. Well, this is related with increasing the power density. But if increasing the temperature typically means that you are targeting temperatures that are not typically in any application. I mean, in an industry, typically waste heat is typically lower temperature. So you have to create the temperature. And where you can create these high temperatures, storage. I think this is probably one of the main applications today, ultra high temperature storage. You can use make very high temperatures in combined heat and power, portable power devices, and indeed this is related with the companies that already exist for TPV, like Antora or Mersodyne, that are working specifically in these applications where you can get those extreme temperatures. The other one is to reduce the cost per area of the device. This is the common strategy in photovoltaics, trying to find cheaper materials. In TPV, I think that there are two options to reduce the cost per area. You can either use low-cost semiconductor, and germanium probably is the semiconductor with a lower cost for TPV applications. Or you can go to exfoliation techniques to make very thin cells, as Andrej strategy basically, to reuse the very expensive substrate. This is the second strategy. And the third strategy is to increase the power density, but without increasing the temperature, which is important to decouple these things. And in this case, near-field thermophotovoltaics, I think, is the way you can get like orders of magnitude higher power without increasing the temperature. But this is, of course, at low level of development. And there are novel concepts. So we shouldn't forget the very novel concepts in TPV. We have thermophotonics, for instance, that you can pump heat from the meter if you have a hot LED and then pump this heat in the form of electroluminescent radiation. Well, there is light pipe TPV. There are novel concepts that can be used to reduce the cost as well.
Okay. We have other questions, but I want to throw a question because this is the one that I want to, I think you all emphasized the high power density. The challenge, one challenge is when you get a very high power density is the cold side thermal management. And of course, say Jared here, you can claim say the advantage of thermionic because you operate at higher temperature. Andrej, have you modeled in the larger scale application, right? What say is the temperature rise of the cell large enough? Say too high. One because of the air gap. Two because of the large power density. And this is even worse in the near field. Let's say that.
Yeah, that's a great question. The air gap, I don't think presents an additional thermal resistance that really needs to be taken into account. I haven't done modeling myself, taking into account the heat transfer, the thermal management side, but there are models out there that, you know, if you look at work from Oscar Henry and his colleagues, I think they've done some work in that space, or at least they're getting ready to publish some work in that space, taking that into consideration. So you make a good point that if we push the power density, not only do we run into ohmic losses, we also run into heating up of the cell. And that's why I think we can only take power density so far with TPV applications. To me, there has to be other ways of reducing, we have to use other ways of reducing the cost using substrate reuse or lower cost semiconductors. I think that's because we can't necessarily reach the power densities that we need to make this very, very cheap. I do want to emphasize though that efficiency is also a really important metric because the TPV cell is only one small part of the overall energy conversion system. And the scale, the cost of that energy conversion system will be driven down if the efficiency is high.
So yeah, just to tap into that question, I want to ask Gerard in terms of efficiency. See, when you call the 10% efficiency, did you include the combustor efficiency?
Oh, for those particular ones, we did not include the combustion efficiency, but it's a very good point that for any of these, if you're operating at high temperature, one of the main areas that will be challenging, unless you're doing energy storage and heating up electrically, is getting the heat at high temperature exactly where you want it, and getting heat at high heat flux exactly where you want it. And that's been actually quite a bit of our effort over the last several months to improve that in our devices. And in fact, our entire device design today is designed around fixing that problem.
Alejandro, you have any?
Yeah. Well, just short comment to add. Well, that precisely as what Andrej said. I think that the cooling issue is solved by increasing the efficiency. So it's not only power density but also efficiency. So if you get a 50% efficient device, you can handle a higher power density, of course, because your cooling requirements will be lower as well. So it's targeting the two metrics at the same time.
Great. Let's take one more question. This is from Terry Hendricks. Terry, I hope you're doing well. So the question is, why is the limitation of a lower power density not a fundamental limitation of this energy conversion technology? So I guess the question is, say, lower power density not a fundamental limit of this energy conversion?
Well, not sure if I understood the question, but I will jump.
I guess to say they really those what from the discussion we have heard, I would say that the power density is not your limitation. So my own experience in the thermoelectric, particularly talking about the waste heat, is actually getting that power density into the device and out of the device that can match the device power density. And of course, Gerard, you mentioned the combustion. That is one example, right? If you do combustion, you have that power density. You have to match that, and how expensive is that system cost? And that's critical. I guess the power density for TPV is because they will be more sensitive to the say cold side, the TPV temperature. So that is something that I think from really the way I say that many times the thermal side is so important in determining at the end we all care about the say dollar per watt, right, for large scale applications. I think say we have other questions. Say I will not be able to cover more. I just want to bring back. I want to thank say our panelists. This is a really interesting topic, and I want to bring back also our next one. I'll not show this slide, but so this is again repeating. This is our last Colloquia this year, and we will start on February 3rd, bi-weekly, Wednesday, same time in 2021. And with that, I want to thank all our panelists again, and I also want to thank our helper students, postdocs, Coco. This online is Xiaoting, and the back is Simo, and also James Zhang and other students. So thank you very much. And with that, since this is the last one this year, so we have say early happy holidays, and hope you all have a safe holiday, safe and happy. Thank you. I will keep the website open for a few more minutes. You can send in more questions, and then they will put all this question on the website and YouTube site. Thank you.